Hi, everyone. The next topic is matrices. So most statistical inferences are better described when we use matrix representation. So in Stat 6840, especially it is important to understand all models in terms of matrices. Maybe the Stat 5800 teaches linear models without using much matrix notations, but here in our course, the matrices are really important. And actually, the biggest difference between newer statistical languages such as R or MATLAB or Ox, Gauss, Python, and older languages such as the SAS or Stata is that the newer languages can deal with the matrices calculation very fast. So now we will have a quick review on matrices in R. Okay, so this is our console, and to declare matrices, matrix, that we can use the matrix function. So if you want to define A as the matrix, you can just specify number of rows and number of columns. And if you want to just create the zero matrix, then you can type in this way. Then we can generate the 2x3 matrices. So you can just change elements of a matrix by using this argument, the A bracket 2, this is the second entry of A, so 2 element of A. So if you want to change it into 100, then we can do this way. So if you leave either rows or columns as blank, then you will get all columns if you don't specify columns. So if you type A1 bracket, then we get the 0, 0, 0. So this is actually the first line of first row of the matrix A. Okay. So yes, we can do it in the same way as for columns. So this is basically the same as A1 to 2. And yeah, and actually the R doesn't distinguish the row vector and the column vector. So A100, this should be row vector, but the R can just recognize is a sequence of numbers. So if you want to, for example, you can see that the row vector and column vector have the same objects. So if you want to recognize, for example, the second column of A as a column vector or a 2x1 matrix, that you can use as matrix, then it becomes a 2x1 matrix. And another way to create a matrix is using cbind or rbind function. So at first you create column vectors or row vectors, then after that you combine. For example, if W is 1, 2, 3 and H is 10, 20, 30, then if you use the cbind function, then we get these two. We bind these two as column vectors, so the column bind function. So we get the 3x2 matrix, and or rbind function. Then we get 2x3 matrix whose the rows are these vectors W and H. And of course, you don't really have to do in 2 steps. You can do in 1 step in this way. So these are matrices. Yeah, so matrix calculation. So we have defined, okay, so suppose that we define this as A and B. as another matrix, such as maybe the 3, 0, 0, 3, 0, 2. Then A and B are this. So A plus B, A minus B, you can calculate this way. But we have to be careful that the A times B is just component-wise product. So it's not a matrix product. So this is component-wise. And if you want to we want to calculate the matrix product, we have to use the percentage, the dollar percentage. So then we can get the matrix product in this way. So yeah, you can double check. A and B are this. So for example, how about this 6? So this is the first row, the inner product of the first row of A and the second column of B. So 1 times 0 plus 3 times 2, so that is 6. Okay, so this is matrix product. And inverse, solve of A. Solve function makes an inverse. So A inverse is this. So if you multiply solve A and A, this is A inverse A. So this is a unit matrix. And other things can be done in the same way. For example, if we have the X vector and we want to calculate the A times X, matrix A times vector X, then we can do this in the same way as matrix calculation. So we have to be careful that the X is a vector, and sometimes, so R recognize this as either row vector or column vector. So A is 2 by 2, so X is regarded as 2 by 1. But if we type X product A, then A is 2 by 2, so X is regarded as row vector. So this way. So R doesn't distinguish row vectors and column vectors. So next, diagonal matrices. If you type diagonal of 3, then we can get the 3 by 3 unit matrix, identity matrix. And if we type in this way, we get diagonal matrix with these diagonal entries. So you can just do it in this way. So the length of the vector determines the dimension of matrix. And transposed A, okay, so A is this. Transposed A is the T of A. And the determinant of A is depth of A. And also eigenvalue of A. You can get this. So actually, the first column corresponds to the first eigenvalue. Second column corresponds to the second eigenvalue. So you can see that the yeah. So you can access this vector by eigenvector of A, eigen of A vectors, and the first column. Okay, so in this way, so this vector. So if you multiply A with this eigenvector, what happens? So this becomes actually 5.37 times larger than this. So negative 0.56 becomes negative 3.03. So negative 3.03 divided by this original eigenvector, this is 5.37. So same thing applies for this. Right, so the A times eigenvector is equal to some eigenvalue times times X. Okay, so these are the basics of the matrices. And just at last, we would like to discuss the row and column names. So matrix A doesn't have the row names or column names, but sometimes you would like to put something. So for example, the rows that explains which patients are malignant, and the columns explains the test results, such as 1 is positive and 2 is negative. So we may want to put that kind of information. So call names A and row names of A. So those two functions can do that job. So for example, column names, positive and negative, and you have to put C because we have to define multiple things at the same time. So we have to declare a vector. So this, and the row names of A, this way. So the A is this way. A becomes this matrix. So we can just name this. So this is still just a matrix, but this name information has been included in A. You can also extract this information by typing call names A and the row names A. Okay, so this is how to handle matrices in R.